In this recording, we will be discussing one of the techniques of data mining techniques, one of the supervised data mining techniques called k-nearest neighbors. Before we start talking about k-nearest neighbors, we are going to summarize the data mining techniques that we have covered and the ones that we are going to cover, and the limitations and the pros and cons for each of them. So first, we are going to have a quick introduction about supervised data mining. Supervised data mining techniques includes, let's try to summarize what we have done so far. So the supervised data mining techniques include either classification models or prediction models. When we talk about classification models, the target variable is categorical. When we talk about prediction models, the target variable is numerical. Examples. When you have a classification models, this includes predicting, for instance, whether or not a customer will make a purchase, or a mortgage will be approved or no, or a patient will have a certain disease or no, or an email is going to be a spam or no. At the same time, examples of the prediction models, including what? Predicting the sale price of a house, predicting the salary of a university graduate, predicting the total sales of a firm, predicting annual spending of a customer. And we discussed in chapters 8 and 7 linear regression models, and these techniques are important for prediction models. So these are examples of prediction models, linear regression models. And in chapter 9 we discussed logistic regression models, and these are important classification models. In this chapter we are going to extend the analysis by including two widely used data mining techniques. So the first one in this section is going to be k-nearest neighbors, and next section we are going to discuss naive Bayes. Also, in the following chapter we are going to cover classification and regression trees and ensemble trees. We may use a term in this chapter which is called scoring a record. Scoring a record is going to be like a process for classifying or predicting the value of the target variable of a new record for given values of predictor variables. So this is going to be like a term that we may use in this chapter. And if you remember, let's go back to some of the problems that we faced before, which is overfitting problem. Overfitting occurs when a predictive model is made overly complex to fit the quirks of given sample data. It's possible for a model to perform really well with the data set used for estimation, but then perform poorly when a new data set is used. So what we did to address this issue is we partitioned the data into training, validation, and sometimes optional test data sets. And what does training data used for? It's used to generate one or more models, while the validation data set is used to evaluate the performance of the models and select the best model. If you already have a test data set, then this will be used to assess the performance of the final model on a new data set. If you don't, you can use just the training, the validation data set. Also, we discussed in chapter 11 performance measures to assess predictive models. We discussed two types of performance measures, one for the classification models, one for prediction models. Right? For the classification, we have something called a confusion matrix. This one is used to summarize all outcomes obtained from the validation dataset. And the outcomes includes, if you remember, true positives and true negatives, where the observations are classified correctly by the model. At the same time, false positive and false negative outcomes imply that the observations are incorrectly classified by the model. Based on these outcomes, performance measures like accuracy rate, misclassification rate, sensitivity, specificity are computed. Also, we have built graphical representations like the cumulative lift chart, decile-wise lift chart, and ROC curve to assess model performance. This is for the classification problems. For the prediction models, the performance measures we used based on something called prediction error, which is the difference between the actual and the predicted value of the numerical target variable. And we have gone over a few of them just quickly. These measures capture the magnitude of the prediction errors. Examples of these are SE, ME, MAD, MAD, and MAE, and MPE and MAPE. In this slide, if you can see that there are many data mining techniques, and everyone has its advantages and limitations. It's recommended that we explore several predictive models based on different techniques and choose the best model based on performance and other practical considerations. And we summarize the key differences here among these supervised data mining techniques. Linear regression, the one we discussed in chapter 7 and 8, it's widely used, computationally efficient, give you the best mathematical function that you can interpret the estimates and the predictor importance information. But the problem with the linear regression is the first problem is mostly used, it's mostly used for the prediction purposes, and it's affected by nonlinearity and multicollinearity issues with between the predictor variables, and we have to check the assumptions like the nonlinearity and multicollinearity and all of this stuff. For the logistic regression is computationally efficient, and we can interpret the coefficients as well. It's not hard to interpret the coefficients. We can find the probability, but the problem it's just for a classification, and also it can be impacted or affected by the multicollinearity among or between the predictor variables. The two techniques we are going to cover this chapter, the first one is the k-nearest neighbors. This can be used for classification and the prediction, but it's more effective as a classifier, in the classification, problems. It's easy to understand, doesn't assume any distribution for the target variable, there's no assumptions. What are the limitations of the K and N? Is it provides no information on the predictor importance and searches the entire training data set. That makes it expensive computationally. The following one that we will be discussing is the naive Bayes. This is simple, efficient, effective, but it's for classification, and there is one assumption that we have to assume, that it assumes the independence among the predictors. The variables are independent. Also, the predictors must be categorical or transformed into categories, and we can do this using binning as we did in chapter 2. For the CART technique, using the tree, so this is the tree works for both classification and the prediction. It's easy to explain. It's not hard. It gives an important information. Doesn't assume any assumptions, any distribution of the target variable. Robust when you're dealing with outliers and missing values. But it captures nothing between the predictor variables in terms of interactions. And it is sensitive to changes in data. Single tree or trees are prone to overfitting. That's why we use unsampled tree models, because we have an overfitting problems with the CART. We use the unsampled tree models to enhance what CART has done. So the unsampled tree is used for both again, and it addresses the overfitting issues for the single trees models. But the problem with the unsampled tree is that it lacks interpretability. It's hard to interpret, and it doesn't give a visual representation of the trees. Linear and quadratic discriminant analysis. These are another nice two data mining techniques that we can use, and they are accounting for the interaction between the predictor variables, but they are only used for classification. And there is one assumption or two assumptions that have to be used here, that the predictor variables have to be normally distributed with equal variances, and it uses only numerical predictor variables. Neural network use both classification and the prediction model. It's flexible, captures complex relationships, and the problem with that, it provides little insight into relationships or results, hard to interpret, and it's expensive in terms of computations. So these are kind of comparison between all of the techniques, advantages and limitations for each. Let's now move to the first one in this section, which is speaking about the KNN. So we said we explore a supervised data mining method here. It's called KNN, K nearest neighbors. It's been used in numerous applications, including personalized recommendations, loan application, evaluation, fraud detection, medical diagnosis. It's simple. Most frequent used data mining techniques for classification when the response variable is categorical, and for the prediction as well when the response variable is numerical. Also, the traditional KNN algorithms require predictor variables to be numerical, therefore data transformation may need to be performed to convert categorical predictor variables into numerical. We did this in chapter 2. It's a very effective classifier, but it's less popular as a predictor, so we mainly use it as a classifier, not as a predictor. So we use it as a classification problems. And we are going to focus on the classification models here, especially where the target variable is binary. The KNN method belongs to a category of data mining techniques. We call it memory-based reasoning. The memory-based reasoning is based on what? Based on that we tend to guide our decisions using the memories of similar situations we experienced in the past. For example, a credit card company can use KNN to evaluate a new credit card application based on what? Information from similar customers. The KNN algorithms treat the existing credit card holders that are most similar to the new credit card applicants as it is nearest neighbors and uses the existing information to determine whether or not to approve the new application. Another example, in the medical field, doctors and nurses can use the KNN algorithm to compare past patients to help determine whether or not a new patient has a similar disease. Past patients with similar symptoms are considered nearest neighbors of the new patient, and their information can be used to help diagnose new patients. Let's look at this example. Consider a mortgage company trying to determine whether or not a new applicant is likely to default on his or her home loan. The new applicant is 30 years old and has an annual income $64,000, and the mortgage company extracts information from 10 previous customers with similar income in thousands. These are in the income. And age characteristics, as well as whether or not the customer defaulted on loan or no. So these are from the past information. So the KNN in this case works by identifying a number of existing observations, in this case past loan applicants, that are most similar to the new observations, which is the new applicant. Why? In order to classify the new observation, we're going to say whether this guy is going to default or no. So the central component of the KNN, we have two components: the chosen similarity measures and the number of nearest neighbors, K, to consider. So in practice, the KNN algorithm often uses the Euclidean distance to measure the similarity between observations. We did this in the previous chapter, how to find the Euclidean distance. And in this example, in the mortgage example, the differences in the scale of the age and income variables, we have differences. So what we do, we standardize these variables before calculating the Euclidean distance between observations. So because you have differences in the scales, so that's why we're standardizing these values. And both of these techniques, we have done them before, how to standardize and how to find Euclidean distances. So this shows a scatter plot of age against income, age and income, for the past 10 customers. And where customers who defaulted on the loan are labeled with red marker, and the customers who did not default are labeled with a blue marker. We add the new applicant here as a green triangle, and we try to identify the 3 nearest neighbors. Why 3? Yeah, there's no reason now why we are doing 3, why it's not 4, it's not 5, why it's not 2 or 1. So this is something that we are going to decide later. What is the number of the neighbors, the K? What is K? K in this case is a 3, so we chose K to be 3. So the nearest neighbors can be also determined mathematically using Euclidean distance between the new applicant and the other. What are the closest to 3 neighbors? We just find the Euclidean distance. So in this scenario, it's clear that only one of the three neighbors defaulted on his or her home loan, because we have one red, right? And we estimate that the probability that the new applicant is going to default is 1 out of the 3. It's 33%. So the mortgage company can then compare the probability to a predetermined cut-off point in order to decide whether to approve or to reject the new applicant. If the company, for instance, uses the 0.5 as a cutoff value, as a default probability cutoff value, the new loan applicant will be classified as being unlikely to default and will receive an approval on the loan application. However, if the cutoff value is 0.25, the new loan applicant will be classified as being likely to default, and we talked about these cutoff values in the previous chapters. So the choice of K may result in different classification results. For instance, if you would like to choose K to be 1, what is the closest 1? So you're going to classify this guy based on one neighbor. Then we use the nearest neighbor, the red marker, to determine the class membership of the new applicant. In this case, the probability that the new applicant is going to default is going to be 100% because we have only one and it's red, right? So because the KNN method is a supervised data mining technique, data partitioning is used to evaluate its performance and to optimize model complexity. The model complexity will be defined in a way that what is the optimal K, what is the optimal value of K that we have to use in this problem. So the nearest neighbor observations are identified in the training data set. We generally experiment with a range of K values, and this is what we're going to do. R is going to do this for you. So we're going to experiment with a range of K values and their corresponding performance measures from the validation data set in order to determine the optimal K value. So we're going to do experiments trying to find the optimal K value after looking at the performance measures. So we use the KNN algorithm to classify new observations based on the existing observations in the training data set that are most likely or most similar to the new observation. And this process, we call it scoring a new record based on the values of the predictor variables. So the KNN first searches the entire training data set for the most similar observation and then provide a score for the new observation. The final thoughts here, and these are important. Unlike traditional analysis techniques such as linear and regression model, the KNN algorithm does not assume any distribution for making predictions, and it's a non-parametric approach that makes KNN very useful in a practical situation because any real-world data do not always follow theoretical assumptions. It is simple, but at the same time, it produces highly accurate results. And because the KNN searches for the entire training data set for the close neighbors, the process can be, as we said before, can be time-consuming and computationally intensive, especially when you have large amount of data. But we have no problem. Why? Because we are using computers to do this. We are using R. So this is KNN technique, and it's really nice and easy. And we are going to go over an example in the next recording.